Okay, so I'm going to give like a 2 minutes overview on Windward. You know, paying for all these pizzas and beers must mean something. Windward is a very unique company in many ways. It was founded 8 years ago by Ami and Matan, two former Navy officers, and their vision was very unique. They wanted to bring visibility. I'm talking about 2010, 11. They wanted to bring visibility to the world, to the maritime world, which was at the time kind of like the Wild West. Very different, for example, from the aviation world. And the company evolved through the years, and what we are doing now is basically we are integrating domain expertise from the maritime world and data science expertise and technology to basically analyze marine risk and predict it. We're doing it in two main verticals. The one that I'm going to focus on today is the security intelligence domain, just helping basically enforcement agencies catch the bad guys. And the other vertical, which I'm not going to focus on today, but it's not less interesting in terms of data science and other data challenges, is the insurance vertical, where we found that our modeling of vessels' behavior is indicative of the chance of the propensity of a vessel to undergo a maritime accident. So this is something that I'm going to briefly touch upon, but I'm going to focus mainly on the intelligence part. It's a unique company because we are doing stuff that was not done before. At least in most of these domains, we are kind of unique in the landscape. People are doing things that are similar, but not quite. And the thing is that we're trying to integrate all this data science and actually make a difference and solve problems that are now underserved, both in the insurance world and the intelligence world. And I hope I'll give you like a taste of what it means in the next half an hour. Okay, so let's go to the main finish talking about Windward. Let's talk a little bit about the Quest. The Quest is an interesting vessel. It's a very unique. It spent most of its life sailing in Scandinavia. I don't know if you can see this. A little bit in the Mediterranean. Around May 18, 22nd, it changed its ownership. It changed its name, as it often happens, from the Sea View to the Quest. It's a very old vessel, built in 1966. It's a relevant fact. After it changed ownership, it started to behave strangely. What it did shortly after, it took off from Malta, did this strange voyage, not entering Algeria, just turning here and going back all the way towards here. Why is it strange? Because merchant vessels are economical creatures, right? Doing this voyage with no apparent reason seems strange, without entering port, for example. And let me show you what happened at this point, in this turn point. I'll just comment on what's happening. This is an Italian border control body. It's called Guardia di Finanza. Basically boarding a vessel, the Quest that we just saw. See all these helicopters and stuff like that, people with machine guns. It's a big operation. They boarded the vessel. If you look, you'll see it's kind of old. It's not maintained properly. And then they started searching. Obviously, you do something like that when you have a concrete lead. And finding illicit materials on a vessel is very hard because it's a big thing. It's 3-dimensional. Behind the water compartment, there was a hidden compartment with 10 tons of hashish, worth a lot of money. And then the Quest was detained and escorted towards a port in Italy. And that is a success story, right? But the problem is, obviously, the Italians had a concrete lead of what's going on this vessel before they launched all these massive forces. The problem is that how do you know which one to tackle, right? This is the Italian territory from, I think, 2 days ago, and it has about 40,000 vessels moving around. And wouldn't it be great if you had this technological oracle that you would pinpoint, would prioritize where to look, right? So instead of giving you data on 40,000 vessels that are moving around, perhaps you can narrow it down for 1%, the top 0.5%, that's like 200 vessels. That is something that a human expert is more likely to be able to cover and to look one by one and investigate. And basically drilling down from this massive amounts of data into something that is more concrete without actually knowing what you're looking for, right? You just want to see them on the map and then start drilling down on the red points, which are the risky vessels, and try to understand why it makes them risky and what you should do about it. So I'm going to tell you about how we are coloring, marking them red and yellow, how we are assessing the amount of risk of every vessel in the world. So the outline of the talk is basically shortly describing the data platform of Windward that was built in the course of a few years, and then how we started tackling building a supervised machine learning model to tackle the risk problems, and a little bit about model interpretability, which is very important for us, and I think it's one of the most talked about topics in the world of AI and machine learning. So a little bit about the Windward platform. So we like to look at it as a pyramid, as a hierarchy of data. We gather data from multiple sources. I'm going to touch briefly upon some of them. It's raw data. It's global. It's historical. We have data for the last 6-7 years. And as raw data usually comes, it's very dirty, right? It's very noisy. We need to know how to clean it and make good use of it. This is the first layer. The second layer, we try to aggregate it and create building blocks of events, right? Not just, for example, location of a vessel or weather at a specific point. We try to basically build, for example, not event like, for example, a vessel entering a port. That's an event that can be queried for, and then can also be used to build features for the machine learning models. So the upper layer is features. Basically, we're building a behavioral profile of vessels that try to capture the ongoing pattern of operation. And the last one is the machine learning models that are basically tackling the core value that Windward's is trying to give its clients. So let's talk a little bit about the raw data. One of the most major sources that we use is called AIS. It's Automatic Identification System. It's a safety protocol, short-range safety protocol, radio-based. I'm not going to touch about all the problems of working with AIS data. It's very noisy. It's very corrupted. This is an example of a Chinese vessel that is masking its actual course. Obviously, it's not sailing through the Sahara and Saudi Arabia. Do you know what's the twist here? What's the manipulation? Can you figure that out? Yeah, it's mirroring, exactly. This is basically going through south of Africa here. So basically change the coordinates of the latitude. But not all manipulations are that easy to capture. It's a very noisy data source, and we spend years of manpower just to be able to work with this kind of data. Another thing that we are very strict on is building a coherent entities of vessels. For example, this vessel changed its name, like ownership, for 3 times, and we need to understand that although it changed its name and some of its identifiers, it's still the same vessel. It's important for us to get the historical context of each entity and avoid fragmentation. Basically, changing of ownership usually corresponds to changing of behavior. For example, these 3 stages of the 3 ownership changes correspond to the 3 different places in the world where the vessel operated. Another thing that is very important for us is the GIS layer, or the polygons layer. We have tens of thousands of polygons that are constantly evolving and changing. For example, new ports are opened, for example, and we need to account for that. And it's a major challenge for us to try to maintain it. You can also learn from the movement of vessels on changing on the mapping, but I won't touch that. I won't get into it now. Other than the GIS layer, we integrate weather data. It's often that strange behavior is explained by weather. For example, a vessel trying to dodge a storm or something like that. So it's a very important context to understand the vessel behavior. So we have data for the last 5 or 6 years on every point of the globe and every hour, and we try to infer events from it. So this is the first layer of the raw data. The second layer of activities is basically taking this raw data that is very hard to work with, one level upwards, and building the building blocks for the next levels. So this, for example, is the first visit of this specific vessel in the Suez Canal. Visiting an area for the first time, it's a deviation from your previous pattern of life. It's an interesting event for us to detect. Another one that is similar to what we saw in the quest is trying to capture this course deviation, this one started from India, from Karachi, went all the way here and back, and this is strange, right? It's a strange voyage. And what is nice is if you make the cross, if you integrate different data sources and you cross them, you sometimes get interesting insights. For example, this is the border of the economical zones of India. So you can see it just made a U-turn just near the border. And that is very typical for vessels doing illegal meetings with other vessels just near the border of the economical zone. So some of the events are just algorithms or simple heuristics, and some of them are machine learning based. For example, we developed a machine learning model to detect ship-to-ship operations. It's a very interesting thing. It's not always illegal, but you can see the pattern of two vessels doing some strange pattern and then sailing one next to each other, basically transferring goods from one to another. So this one, for example, is a supervised model that used thousands of labeled samples to train and to detect this activity, this event. Another thing that is interesting is vessels going dark, turning off all of their transmission, which is obviously a red flag. So first we need to detect whether the turning off of transmission is indeed an intentional thing, or is it like windward's reception problem, right? So we need to detect intentional turning off, or intentional going dark. And then we need to think what to do. This is a very nice example of two vessels meeting one another and then turning off their transmission simultaneously, which is very interesting for us to detect. And then what we usually do, we move to another sensor. We are cooperating with a very cool company called Planet. Planet has I think it's 180 nanosatellites about this big, and they capture imagery from the entire Earth every day. And they have this very cool API. You give them coordinates and a time of day, and then give you the tile. And when we did this to track these two fellows, we saw them both connected. These are two oil tankers, part of a smuggling network of oil from Libya to Syria. We get the entire context. We know this is usually a repeating pattern. We know that one of them continued to Syria, and so on and so forth. So if we continue, another interesting thing is that since we monitor the entire globe, we can look at areas and infer things that are happening in specific areas. This, for example, is another activity that I haven't described of drifting. Just turning off the engine and waiting, and we can cluster them in an unsupervised way to detect the common areas of drifting, right? And then we can detect the outliers that are outside of these areas. And that's an interesting feature as well, or interesting indication as well. So looking at areas is very interesting. Just another example. What you see here is the meeting operations between fishing vessels and reefers. Reefers are like big refrigerating vessels that take the fish from the fishing vessels and bring them to port. And what is very interesting here is to see this cluster here. This is Norway, and this is Russia and Finland. And if you put the context of the polygons of the economical layers, you can see that it's all happening in international water. What's basically happening that fishing vessels go, discharge their cargo, the fish, and then go back fishing, and it's usually an illegal operation because you usually get a specific amount that you can fish. They do it in international water and then go back fishing again. So looking at areas can give you strategical insights of what's going on in the world. So that's the next layer is basically taking these events and calculating features, long-term features that describe the vessel's behavior. So that's moving from taking one-time events and aggregating them to do statistics. For example, the time that the vessel spends in port or sailing over a long period of time. And this basically, the set of features basically gives you like a unique fingerprint or unique signature, behavioral signature of each vessel in the world. And that is the building blocks for our machine learning models. An interesting thing that we can do is basically compare each vessel to its comparable category or its reference populations. For example, we need to compare the operation of an oil tanker to all the oil tankers in the world, right? Because oil tanker is very different from a fishing vessel in its behavior. So what we usually do, we just compare the distribution or compare the specific point relative to the comparable category of the specific vessel, and that also gives an indication if something is off, or is it the same as the rest of the similar vessels that are operating at sea. Okay. So basically, we worked hard. We've built dozens of events. We've built hundreds of features on them, and we have the building blocks to work with. And now we are able to start doing the modeling. And up to 2 years ago, I think 2000 and maybe 3 years ago, 2016, we were somewhere over here. We had a great toolbox that drove value if you knew how to use it. Our in-house domain expert did marvelous thing with this toolbox, but our clients didn't. 3 reasons. First, you had to know what you're looking for. Second, you need to understand the maritime domain. Not all of our clients are familiar with all these intricacies. And third one is you had to know windwards data, right? What does course deviation even mean? So in order to bridge the gap, we thought it would be great if we had this oracle, this genie, that would just tell you where to look. I don't want to compose complicated queries. I don't know what the pattern really is. I just want you to tell me, right? And then we started a side project. I can talk a lot about how the side project evolved, but I'll just go over it briefly. We started with a mock as part of the planning. Usually people don't do it. They just rush to start optimizing or start working or coding. And a big part of the planning phase is actually imagining how the end result would look like. And we thought that if we had this oracle, this genie that would give risk ranking for every vessel in the world, that would be great. And the distribution would probably look like this. And then we thought, what would interest our clients? So it's probably this long tail, right? Our law enforcement customers are not interested in the well-behaving vessels, which are most of the world. They're interested in the cream of the crop. And so after and this is very important because it focuses on what to optimize, right? The optimization metric is very important, and it can be derived from this. Other things that we had to measure and decide on is, for example, we knew that we wanted to be precision-oriented, right? Because if you give a tip to a client and he send an helicopter and there's nothing there, then he'll be pissed. But if you don't give him a lead that actually had the drugs, he won't blame you that you didn't catch everything. So we knew that we had to be precision-oriented. We had to talk about latency. I mean, how dynamic the score will be, and all this kind of consideration that really helps to focus you during the project. The problem is that we started with no label data at all. There is no easy sources of, for example, smuggling databases that you can obtain. It's really hard. And then what do you do? So first of all, you start gathering, blog posts, news sites, start crawling the web, and start gathering. And then you just have to start simple. I think the first version had like 8 features, and we did like a linear combination of them and just sorted and ranked them. And then we showed it to one of our domain experts. Who's sitting here, Omid, and out of the top 30 that we showed him, he knew like 20, right? And if you show it the domain expert, so I know this vessel, it's first a good sign that you're on track, and it also occurred to us that instead of just using them to confirm, perhaps we can use them to generate label data, right? So even if it's their subjective opinion, it's pretty close to reality. Most smuggling cases, for example, are never caught. So we had a lot of challenges of how to deal with it. We had many people, in-house experts, creating label data. We generated a feedback loop from within the product for internal users to be able to mark a specific vessel as risky or not risky in a effortless manner. And then we had to clean this subjective labeling in different ways. For example, we had a super inspector that actually made pass on all comments and all the tags and threw some garbage out. But anyway, this subjective labeling gave us a huge boost with respect to our ability to develop a supervised model. One of the challenges that we had to tackle is that we had many training examples. Once we gathered a few hundreds of cases, we had like many training examples from different points of time, like smuggling in 2015, and we had to generate all the feature space as of 2015, right? Because that's the point where we're interested in the behavior. And we had many, many sparse examples in the time continuum, but the online prediction goes every day. We wanted continuous prediction to work in batches every day, and sometimes the engineering here is different. So if you want random access, you go to databases. If you want like prediction in huge amounts of data, maybe you should use other methods. One of the things here is that this is very biased with respect to this. So for example, the amount, 99 of the vessels are behaving well, right? But our training set was very biased towards the risky vessels. So you had to correct for that in some manner. So one of the things that we tried to do, so we had a problem. Manually labeling a good vessel is boring. I mean, they're just acting like vessels. There's nothing interesting happening, and there's a limited amount of normally behaving vessels that you can give a person to tag for you. It takes time and effort. If it's something interesting, then he's all in it. I mean, wow, that's interesting and that's risky. So what we did, we just tried to random sample the population if 99% are indeed good. So let's just randomly take most of them and give them a label of negative or well-behaving. It might hurt a little bit the signal, but it might also help the model. The things that we didn't take into account is that random sampling is hard to do in a truly random way. And we just took a batch of random vessels from a specific date. And it turns out that it bites us. Of course, we saw too good to be true results, right? You need to develop the intuition where it can be that good, right? It's very important in data science. And then we digged in a little bit, saw the feature importance of some features, and then we saw that some of our features are time dependent, right? For example, the feature that we had, how many days the vessel exists in our system, is slowly shifting to the right as you go through the years, right? It's the same distribution, just shifted to the right. And what the model did, it basically exploited this leakage, right? This feature enabled the model to learn the specific date where most of the data is negative, and it just exploited the leakage. So we had to fix the feature, and we also fixed our sampling process to be more random on different dates. But that's something to be aware of, to be careful. And then another thing that we understood is that we don't really want it to say yes or no, and we are afraid to give probabilities for the events. It's really, presumptuous to say this vessel has 27% of smuggling now. So what we did, we used a classifier to rank, right? We took the probabilities of the model, for example, the XGBoost classifier that we trained, and basically ranked the entire population, and then took the top X%, let's say a prior of 1% of the world population is interesting, and just ranked it and took the top 1% or X%. Working with XGBoost, when you want to rank, XGBoost has like tons of parameters you can optimize and tune, and two of them are really interesting. So first is the eval metric. So remember I showed you the mock. So raw KUC is not a good metric if you are only interested in the edge of the distribution, right? No one is interested in if you are sorting the middle of the population. So one thing that you can do, you can replace the raw KUC eval metric of the XGBoost to a custom function that actually does that, right? Takes the top 5%, 2%, 1%, and checks precision on that, for example. And another thing that is worth playing around with is changing the objective function for something more suitable to ranking, and not, for example, I think don't remember the default. I think it's logistic. I think it's binary logistic. For the objective function, just a reminder, objective function is the function that the boosting algorithm calculates in each iteration when it builds the next tree. So we had to play a little bit around with that. And another thing that we saw is that the world is changing. We did the model on different time points, and we saw that there is a gradual decline in this is the percentiles, the different percentiles. This is the 98th percentile of the predictions, and it's slowly decreasing. And there are a couple of explanations here. One is the features bias that I just showed you. If you have features that are slowly decaying or shifting the distribution, that can explain that. And the other explanation is that sometimes the population is changing. So for example, if we inserted a lot of good or safe vessels, then the percentages will also shift, okay? So just to see that you're not falling asleep, a midterm quiz to check your intuition. What do you think is the most discriminating feature that will enable to detect smuggling, for example? The vessel age, the number of countries that it visited, the type, or the size of the vessel? I think the type is very interesting, but the actual answer is the number of countries. Well, it turns out that local vessels don't smuggle, right? They don't leave the country, and it's a big part of the population. It seems trivial, but this is the thing that you say that you couldn't think of it beforehand, and then you see it in the data and say, oh wow, it's trivial. Of course, it's a storm feature, but no one knows it in advance. A little bit about model interpretability. It's a very huge thing, especially last year. How many of you know Lime? Heard of Lime? Okay, most. SHAP? Okay, fewer. So a little bit about model interpretability in general. So first, it's obvious why our model needs explanation, right? If you're going to raid a vessel in the middle of the ocean, you need to understand why. If you are trying to insure a vessel or not insure a vessel, you need to understand why it's risky. And it's the same for every critical decision-making based on machine learning model in medical domains and so on. So I like to divide it into two. So the first is the technical debugging tool for a data scientist. And the second is the product integration for the end user. I'm going to talk a little bit about SHAP, which is a technical tool for the data scientist to inspect its model. So SHAP basically is an algorithm that lets you understand the impact of every feature, every specific feature on a specific example. I don't have time to explain exactly how it works, but basically it calculates. There's a great book about interpretability here, which I suggest you guys read. It's not just about SHAP, about the topic in general. Basically, it just calculates different permutations of the different features and compare them with the features at hand to understand the contribution of the feature that it isolates. Basically, it runs many experiments. It has very nice properties. For example, completeness. What it does is all the SHAP values or the contributions of features generate, when you sum them up, it's basically the distance from the average prediction, so either to upwards or downwards. Dummy means basically if it doesn't affect the prediction, the SHAP value will be 0. And additivity means that you can take SHAP values of different algorithms and add them. For example, it's very good for tree-based models. For example, random forest, if you average different decision trees, you can concurrently, in parallel, calculate SHAP values for every tree and just sum them up together. Just to show you how it works, so basically this is the code. It's a very simple code. Works very well with most of the sklearn models. So what you see here, this is the average. This is the average prediction of the model, and this is the actual prediction for a specific sample. So this is the quest, which was very dangerous. The vessel that we started with, and all the red ones are pushing the prediction to the right, and all the blue ones are well-behaving features that are pushing the predictions towards the safer area. And you see that the red ones are bigger. And indeed, the build here that we talked about, it's an old vessel, it's more disposable, it's a risk indicator, pushing it to the right. It visited new places, pushes it to the right, and so on. So it's a very good tool for data scientists to inspect specific samples, similar to what you do with Lime, but I think it's even more easy to understand. Another thing that you can do is basically inspect the entire data set. So for example, what you see here is the SHAP value versus the feature value to see correlations, or the gradient, or the correlation between the feature value and the contribution to the model. So for example, if I take the turning off transmission, the going dark, if you don't do it, meaning that the feature value is low, then you're good, negative SHAP value. If you're doing it, then it becomes red, meaning that you're contributing to the risk. So if you have monotonous features, that's easy. Some features are more complex. For example, it's red in both, in the middle it's safe. Then you need to understand what's going on. Maybe it's dependent in other features, and you can do also all sorts of dependence plot with SHAP. It's a very useful tool. I suggest you guys just pip install it, and you will discover interesting things in your models. Just to sum up, so basically I just described the Winward's data platform as a hierarchical way to work with raw data. You just build the building blocks, then you create features from them. Talked a little bit of interesting challenges that we had when we just started this risk modeling project of doing imbalanced data with no label data at the beginning. And SHAP is an inspection tool for model interpretability. Just want to thank the team. All of them contributed to the work and the specific presentation. I would specifically want to mention Yohanan, who was an intern, who started the project in its early stages with me, and Noam, which is our chief domain expert. You can say that our risk model is the most similar to her brain, because he is responsible to most of the samples. We're also hiring a senior data scientist and a technical data analyst. So if you know someone that is looking to do really meaningful, interesting stuff, talk to us. There are many Winward people in the crowd. If you want to see the system during the break, see the actual things that we're doing, you're more than welcome. And I'll be happy to take any questions that you have. Yalla, Ken.
What is the scale of your data set?
Okay, so the bottom layer of the raw data, it's like hundreds of million data points a day. It's in gigabytes is I don't know, 100 gigabytes a day. But one of the challenges is that we need to calculate all the historical data in retrospect. So for example, if we generate a new algorithm, we want its prediction on the entire history for all vessels in the world. So what we do basically every weekend, we just rerun history again. All of the algorithms are recalculated on the historical data. Sometimes it's a huge engineering challenge, but it enables us to improve the algorithms and enjoy the fruits on a global and historical scale.
But this is on your raw data, on your feature extracting data. When you start using machine learning, what is it?
So it depends. With the risk model, for example, we started with no label data, so you need just very strong and simple features that might show a signal. So it usually in the end models it could be tens of features. In the insurance, and the data set, it depends on, so again, how many smuggling events. So it's a few thousands. Yeah. But it took us a lot to reach that. Yeah.
What do you do with faulty AIS ships? There are a bunch.
Yeah. So basically that was the bread and butter of Winward the past few years. We have algorithms to detect which vessel is manipulating its AIS, to throw away noisy data points. It's a lot of algorithmics involved. And we have also an hybrid system in which where we're not so sure, I mean, there are some cases that are very difficult, then we give them to a human expert. So we have a human expert going over about, I don't know, 30, 40 cases of AIS manipulations a day, which are very hard for the algorithm to decide what's happening, and it just gives this feedback to the system.
In your model, each observation data point is per vessel?
It's per vessel per time. So it's possible for a vessel to appear more than once in the data set.
So can you capture complex interaction between different vessels?
Yes, so we have a very nice project of basically taking this feature space, you can call it ship to vec, right? Representing the behavior of the vessel in a vector, that's what it is. And then we can do some very neat things with it. For example, you can do some k nearest neighbor and get similar behaving vessels to the one that you are actually investigating. You can do clustering and outlier detection when you have this n-dimensional signature. So yeah, we are looking at interactions. We are doing a little bit of graph analysis. I just didn't have time to show the full stack.